Warning, what you are about to hear cannot be unheard. You will hear two piccolos screaming out the first four measures of a late 90s alternative rock song. In the dense fog of this shrill cacophony, if you listen close enough, you will hear a much lower tone. This tone is a Gestalt manifestation of a heretofore unexperienced psychoacoustic phenomenon. The Heterodyne All-Star. Are you ready, eager viewer? Are you ready to test the limits of your own perception and bathe in the glow of phenomenological discovery?
You just heard, or more accurately, were subjected to a demonstration of something that Arthur H. Bonnard refers to in his book, The Fundamentals of Musical Acoustics, as heterodynes, also known as Tartini tones, and most commonly combination tones. What are these things? Well,
Part 1. A brief history and description of these things.
Tartini tones are attributed to 18th century violinist and sometimes friend of the devil, Guiseppe Tartini. He first noticed them while he was practicing double stops, or two notes played at the same time. While doing this, he noticed that he could hear a faint lower tone. He called this tone il terzo suono, or the third sound. When two notes are sounded on a violin or any other combination of instruments, your ear should hear two notes in the respective overtones, right? Well, it doesn't. It hears a lot of other non-harmonic tones. Your inner ear is non-linear, which means that it hears the sum of and the difference between two separate frequencies whenever you hear them. These sum tones and difference tones can sometimes be quite faint, but they are always there when you hear two or more notes. I asked my friend Brian Krock to play the beginning example on a piccolo, because combination tones are easiest to hear with high, loud, and pure sounds. Very often this is done electronically with sine waves, but the closest instrument to doing that sort of thing is a piccolo. I also asked Brian to do an experiment of sorts to see what kinds of combination tones are possible. Listen carefully as Brian plays a steady C natural on one track, and then also listen to how he ascends chromatically on the other track. You should hear a low tone, the difference between the two tracks.
Combination tones can only really be heard at moderate to high volumes, so please turn up your volume and hope that anybody that you live with is into learning about psychoacoustics.
You might notice that as Brian ascends by half step, the combination tones ascend by much larger intervals. Very close generating notes produce lower combination tones, and wider generating notes produce higher combination tones.
Okay, that's cool, I guess. But what's the practical application in all of this? Why should we care?
Great question.
Part 2. Why should we care?
For starters, combination tones are used frequently for checking if you're in tune or not. Tartini himself used it as a means of checking his double stop intonation. For that reason, combination tones are often thought of as a form of acoustic beat, a pattern of destructive interference between two waveforms. You see, pitch is determined by Hertz, or cycles per second. When you hear music, your inner ear detects hundreds of cycles per second, and then your brain perceives that as pitch. When you have two cycles which are slightly different, or rather, slightly out of tune, you'll get an acoustic beat. Every time one cycle is compressing air, while the other cycle is rarefracting it or expanding it, they cancel each other out. And so you hear a fluctuation in volume, otherwise known as a beat. Right here, I have two sine waves, both at 300 Hertz. If I change one of the sine waves to vibrate at 302 Hertz, you'll hear a very steady 2 Hertz beat, the difference between the two sine waves. You could actually time this out with a metronome. 2 Hertz is twice per second, otherwise known as 120 beats per minute. Timing acoustic beats with metronomes, by the way, is how piano tuners tune pianos. They'll listen for the acoustic beats between two strings and then time out using a metronome to figure out exactly how many acoustic beats per minute are necessary for our equal tempered system. They literally use rhythm to tune pitch, which I think is a fascinating example of this idea that rhythm and pitch are the same thing. Because we perceive pitch as cycles per second, and we have these acoustic beats between two different pitches, if those beats are happening fast enough, we in theory should hear an additional note. That's the theory, anyway.
It's actually likely acoustic beats aren't the cause of combination tones. Something else is. Something much weirder. We'll get into that later.
Okay, I think I get it, but is there some kind of metaphor that you can use to, kind of oversimplify things in order to explain it to me, like science fiction writers do all the time?
Part 3. Forced metaphors.
Well, I wouldn't call it a forced metaphor per se, but you could think of combination tones as a sort of musical Moiré effect. The Moiré effect is a visual interference pattern created by two similar repetitive images overlapping one another. As one pattern of stripes overlaps the other, you can see a pattern of moving diagonal lines emerge. These lines don't actually exist in the strictest sense. If you take away the two sets of lines, the moving diagonals go away. If instead of lines you had pitches and they created a combination tone, is that combination tone the same sort of thing? Is it just an illusion created by circumstance, or is it real?
It depends upon what the meaning of the word is. Yes.
Bill Clinton raises a good point.
Part 4. Bill Clinton raises a good point.
Let's record the interaction of two tones interacting in physical space. I'll set up two speakers, each playing a track of piccolo, and then place a microphone between them as I play the original example from the beginning of this video. If they combine in the real world to produce a combination tone, we can pick it up on the microphone, and it will show up in the spectral analysis. It turns out, it doesn't show up in any sort of spectral analysis. When we isolate the lower frequencies, the frequencies that we would expect to find a combination tone because of our mathematical calculations of it, we only hear the breath noise from Brian. If the notes truly were acoustic beats interacting in the real world, we would not need to hear the higher frequencies in order to perceive the combination tone. But the tones don't combine, and so we don't hear it. This brings up some questions of emergent properties. If our inner ear can detect it as music, but microphones can't, is it the same music? Does the music that we listen to only exist in our heads, or does it need to exist out in the real world for it to be considered music? These questions are interesting from a philosophical standpoint, but they're also quite non-trivial from a legal standpoint. The video that you're watching right now might get dinged for copyright infringement by the Universal Music Group, the group which owns the publishing rights to the 90s alternative rock song that you heard at the beginning of this video. Or you might have heard at the beginning of this video. I don't know, the law isn't particularly clear on psychoacoustic phenomenon.
All right, all of this is cool, like the philosophy, the law, the acoustics, all that stuff, but is there any practical musical application for any of this, or is this just some weird quirk of acoustics that you wanted to ramble on about for a while?
Well, this is the exciting stuff, I think. There are a bunch of possibilities here.
Part 5. Actually making music with this stuff.
Combination tones are at the heart of something called sung multiphonics. If you sing a note into a woodwind and brass instrument as you play another note, your ear will hear the difference tone as a composite with the same timbre of the instrument that you are playing. This is most effective when you sing a note a perfect fifth above the note that you play. The resulting difference tone is a note 1 octave below. Derek Brown of Beatbox Sax is a great tutorial and demonstration of this technique, effectively turning an alto or tenor saxophone into a baritone saxophone. This is the same principle, combining fifths to get a lower octave behind something called resultant tones, combination tones on pipe organs created by calculating the differences between pipes. The pitch of pipe organs is determined by the size of the pipes. The largest pipe organs in the world use pipes of up to 64 feet in height to create earth-shattering bass tones down to 8 Hertz. But 64-foot tall pipes are not particularly practical. Lower tones can be simulated by combining shorter pipes to fool your ear into thinking that it's hearing notes lower than it actually is. But your ear isn't completely fooled. After all, the sound of a 64-foot pipe organ pipe sounds like, quote, a helicopter hovering over the building, a physical force that envelops your body rather than your ear. Resultant tones are distortion effects in the inner ear, so they don't affect the body in the same way as hearing actual low notes. Your ear might hear a lower pitch, but your body won't feel it. The nonlinear effects of the inner ear go quite deep, and recent scientific studies have unearthed something called Otoacoustic Emissions, very quiet sounds generated by the ear itself, either spontaneously or in response to stimulus. There are several different kinds of otoacoustic emissions, but the ones that are most useful for us as musicians are distortion product otoacoustic emissions, which are created by the sum of and difference between two sound sources. In other words, sounds that your ear actually makes shakes in response to combination tones. So in order to answer Bill Clinton's burning question, yes, combination tones do exist out there in the real world, just not as acoustic beats. Instead, they exist as otoacoustic emissions from the ear itself.
The fact that we need to listen at high volumes to perceive combination tones is likely because those are the sound pressure levels necessary to stimulate the ear and produce otoacoustic emissions.
The fact that they're so localized to our head and to our ears is something that composers have exploited with a technique known as perceptual geography, a term invented by electronic avant-garde composer Maryanne Amacher. Among a variety of other interests, Amacher was quite interested in working with combination tones with sound installations and speakers played at loud volumes. She would write, "When played at the right sound level, which is quite high and exciting, the tones in this music will cause your ears to act as neurophonic instruments that emit sounds that would seem to be issuing directly from your head." One example of her work that directly exploits this phenomenon is her Chorale No. 1. Chorales are normally plaintive works written for church choirs to be sung, like hymns. Unlike church singers, however, the singers of her chorale are our inner ears. Her strange music is just the stimulus to get our ears to generate these otoacoustic emissions.
Tones that we make as human responders, there really are response tones. When we're experiencing music, we are creating other tones that go along with the tones that are sounding. We are making these tones and we're totally unconscious of all of this.
Her chorale is on her album Sound Characters, Making the Third Ear. Like Tartini's third tone, Maryanne Amacher's music expands what music can be. These combination tones and otoacoustic emissions are at the vanguard, and for the young, intrepid musician might represent some new horizons in music. One of Maryanne Amacher's contemporaries, the composer George Lewis, would write this of her work. "It had texture, it had ghost things inside." I think she actually said, "You have to listen for the ghosts." And then once you started hearing them, they were always there.